Hi, I'd like to show a brief demo about how processes make use of their virtual address space and how this interacts with the linker. Suppose I have a program here where there's a global variable defined with static file local scope. I assign a value, and here I'm outputting the address with the ampersand operator where this global variable is stored. If I build this program and if I'm running it, we see that it is located at some address. If I run it again and again, you'll see that every time I run it, it is located at the same address. Now here I run these processes in series. What if I run them in parallel? Let's say as background processes. We see that no matter how many processes I am running, this particular variable will be located at the same address. And this is what we mean when we say that processes have their own virtual address space. They all can make use of the same address, even though the variables that they access are different because they're different instances of this program. By the way, this also doesn't change if I add a fork. Let's say if this process is going to fork, and then look at the address of the global variable in the child and in the parent process. Okay, so um, if I run this and if I build it, then we will observe the same effect that now the parent process and the child process, in both of these processes, this particular variable is at the same address, even though those are separate variables that can be separately assigned. Now, let me extend this experiment a little bit and look at more than just a single static global variable. So did a small experiments and added a few more variables. I added variables that are global variables that are global in scope, not static. I added some that are not program initialized. I added some that are program initialized. And I added global variables that are local in scope. They have file scope from the linker's perspective. They are called locals, right? Um, and some of them are initialized and some of them are initialized. And in addition, I added a global variable mutable car pointer that points to a character, um, to a string literal. And a string literal is in C, it means the address of the first character. And then the second one, I added a const keyword here so that this pointer cannot be reassigned, right? The first const in this stands for the fact that the characters that are pointed to are not mutable. Um, and this is true for this one and this one because in the string literal I cannot override these characters. But this const stands for the pointer itself not being assignable, right? So it's not possible to say a mutable car pointer is equal to something else, okay, after this initialization. And then I added more things. In the main program, I defined a local variable. I also have this argument that's being passed to main. I print out the address of where it is located. So I'm printing out these addresses as well as for all the variables that I have defined. And in addition, I am also printing out the address where the main function is located. So in C, I can just use the name of a function as a pointer to it. That is the same as specifying this. And finally, I allocate 1 byte on the heap and print out where this is located. So if I am building this program and I'm running it, we see some results. And what I'm going to do is I'm going to run those through the sort program and reverse the order so we can see the order here as if those were alphanumeric strings. So what we see here is in brief the layout of the address space of this process. The Near the bottom, we have two symbols, main and this string literal here, which are in the text segment. I note that the heap here, this is an artifact of the sorting. This address is really, somewhere between those. Um, so we have the text section here includes, for example, the main function, and also string literals such as the CS3214 actually also, even though they're read-only data, they're typically placed into the text segment as well. So then comes the so-called read-only section where we only had this const pointer that goes here, and this is in the 600,000 range. Then come the global variables that have an initial value. So these the four with global scope and these here with local scope. And this mutable car pointer also was an initialized value. After that comes the so-called PSS segments. So those are the global variables that had an initial value of 0, and they are allocated separately because for those, the values do not need to be stored in the executable. Um, and then would come the heap here that would actually sort in here. And then further up, we have the stack in this. Now let's see when we run this multiple times, which values stay the same and which values change. Okay, so when we do this, what we see is that the values for the main function, those globals and so on, all of these here, they stay the same. For example, the strong global here is the same as this, and so on. But the values that change are, for example, the ones for the heap. We have this heap at this address here, and now we have this heap at this address. What also changes is the value for the stack. So if I, for example, just look at the stack, we see that those change every time that this program is run. So some areas, regions of the virtual address space are subject to randomization. A different value is picked every time the program is run. Now, but others are not. So in this case, for example, the global variables and so on, they stay at the same virtual address every time the program is run. Now, I tricked here a little bit in that if you notice this, when I compiled this program here, I actually specified a switch, and the switch here is called no pi. And the reason is that on the system on which I'm demoing this, by default, position independent executables are enabled. So if I compile this by default, what we would see in this case, we would see that not only are the stack and the heap being randomized, but in fact the location of the entire program is randomized. Okay, so here everything changes between different runs. But what we notice is that for the text segment, the data, and the PSS segment, really what changes is just the base where it's located. So the relative offsets between those do not. It is just relocated to a different address. In fact, there is some information that is stored in the executable that allows us to do that. These are these so-called relative relocation records. They perform further relocation at the point in time when the program is loaded. Most of the code is compiled in a position independent fashion, but a little bit of relocation has to be done when the program is loaded. On the machine I'm demoing this, it's an Ubuntu machine. Position independent executables are the default. On other systems, CentOS 8, for example, as of the time of this recording, have a default of NoPy. Okay, and you can with DCC you can specify -NoPy if you don't want position independent code, and you can specify pi if you do, and depending on the system, one or the other may be the default. When you debug, you may encounter faults at certain addresses and you want to reproduce this, then I recommend that you compile your code with NoPy so that you do not get the effect of having different addresses each time you run the program.